Have you ever looked at your reflection in a spoon and just wondered, what is going on here? Well, it's not magic, I promise, it's physics. And today, we are going to dive deep into the really fascinating world of spherical mirrors to figure out exactly why.
All right, here's the game plan. We're going to start with the absolute basics of what makes a mirror curved. Then we'll get into the 4 fundamental rules that tell light where to go. After that, we'll see how those rules play out with both concave and convex mirrors, check out where you see these things in the real world, and finally, we'll even tackle the simple math behind it all.
You know, you probably don't even need to leave your kitchen to find the perfect tool for understanding all of this. It's probably just sitting in a drawer right now.
Yeah, it all boils down to one simple thing. A spoon isn't flat. And because its surface is curved, it bends light and your reflection in some really interesting and totally predictable ways. So believe it or not, a single spoon actually shows us both types of spherical mirrors. The side you scoop soup with, that's concave. It caves in. You can remember it that way. Now flip it over to the bulging side and bam, you've got a convex surface. These two are the main characters in our story today. Okay, to really talk about these mirrors properly, we need to learn the lingo. Don't worry, it's pretty straightforward. First, imagine a straight line running right through the middle. That's the principal axis. The exact spot where that axis hits the mirror, we call that the pole, or just P for short. Now, since every curved mirror is like a slice of a bigger sphere, the center of that sphere is the center of curvature, or C. And maybe the most important part of all is the principal focus, F. This is the magic spot, the point where parallel rays of light all meet up after they bounce off the mirror. All right, let's build on that. To figure out what an image is going to look like, you don't have to trace every single light ray. That would be impossible. Turns out you only need to know 4 super simple, totally reliable rules. These 4 rules are basically our cheat codes. Seriously, by just drawing 2 of these rays coming from any object, we can pinpoint exactly where the image will show up, how big it'll be, and whether it's right side up or upside down. Okay, rule number 1, the parallel ray. This one's easy. Any ray of light that comes in straight, perfectly parallel to that principal axis, is going to get bounced by the mirror right through the principal focus, F, every single time.
And now for rule 2. Check this out. It's the exact opposite of rule 1. If a ray of light passes through the focus first, before it hits the mirror, it bounces off going perfectly parallel to the axis. It's just a perfect, beautiful symmetry.
Rule 3 is probably the easiest one to remember. Any ray that goes through the center of curvature, C, hits the mirror dead on at a perfect 90-degree angle. So what does it do? It just reflects straight back along the exact same path it came from. Simple as that. And last but not least, rule 4, the oblique ray. Any light ray that hits the pole, that's P, the very center of the mirror, is just going to bounce off at the exact same angle but on the other side of the axis. It's like bouncing a basketball on the floor. The angle it comes in at is the angle it leaves at. Okay, now we've got our rules, we can basically predict the future. Of light rays anyway. Let's put them to the test with the concave mirror, the cave side of our spoon. So let's see what happens if we put an object way out there, beyond the center of curvature. We just need to trace 2 rays. Let's use rule 1, a parallel ray reflects through the focus, and rule 3, a ray through the center of curvature bounces straight back. Now look, right where they cross, that's our image. And what do we see? It's smaller, it's real, and it's totally flipped upside down. But hold on, watch what happens when we move the object super close, even closer than the focal point. The rays that reflect off the mirror actually spread apart. They diverge. They're never going to meet out here. So our brain does this amazing trick. It traces the rays backward to a point behind the mirror. And what it sees is a huge, upright, virtual image. It's an illusion. And it's exactly how your makeup or shaving mirror works. So the takeaway here is that a concave mirror is kind of a chameleon. I mean, depending on where you put the object, it can shrink it, enlarge it, flip it, or create this virtual copy. This chart right here summarizes all 6 possibilities and really shows you just how incredibly versatile this thing is. Okay, let's switch gears and talk about its simpler cousin, the convex mirror, the bulging side of the spoon. Its real power isn't in being a chameleon, it's in being incredibly predictable. You know, here's the key thing to remember about convex mirrors. It literally does not matter where you put the object. The result is always the same. The light rays always spread out, and our brain always traces them back to form an image that is smaller, upright, and virtual every single time. So this isn't just a bunch of abstract physics, right? These ideas are working all around you every day. So let's connect all this back to the real world and see why it actually matters. That special ability of a concave mirror to focus light into a single, powerful beam? Well, that's why it's in your car's headlights and in flashlights. And its power to magnify things when you get up close? That's why it's the go-to tool for dentists and why it's in those makeup mirrors. It's all about focusing or magnifying. And this right here is the power of the convex mirror's consistency. Because it always shrinks the image, it can cram a much wider view into a small space. This is perfect for those big security mirrors in shops and, you guessed it, for your car's passenger side mirror. It's what gives you that wide, safe view of the road behind you. Okay, so we've seen how ray diagrams let us predict what images will look like, but sometimes physicists need way more precision. And for that, they use a surprisingly simple bit of math, a secret code, if you will, to get it perfect every time.
All right, let's try a typical problem. This might sound a little technical, but trust me, once you know the secret code, it's unbelievably easy to solve.
The formula itself is dead simple. The focal length, which we call f, is just the radius of curvature r divided by 2. That's it. The only little trick you have to remember is something called the sign convention. It's just a rule. For concave mirrors, we always treat the radius as a negative number. So for this problem, we just plug in -20 for r, do the quick division, and we're good to go.
And there you have it, -10 centimeters. The number 10 tells us the distance, and that little negative sign, it immediately tells any physicist, hey, we're working with a concave mirror. See, it's a clean, precise language that's all built on some really simple math.
So here's the big idea to take away from all this. Spherical mirrors are just a perfect example of how controlling the path of light lets us completely reshape reality. We can magnify, we can shrink, we can see things that would otherwise be hidden. And this fundamental principle of bending light, well, it doesn't just stop at mirrors. It's the very foundation for telescopes, microscopes, and yeah, even the lenses in your own eyes.